Here we go, class. We're going to open up a whole new kind of problem that you can do now that we learned about the definite integral. So remember first semester we talked about our whole goal was to find the slope of a tangent line. So at the beginning we approximated the slope of a tangent line by finding the slope of a secant line. We thought, well, we can make our approximation better, take the 2 points closer together. And if you want an even better approximation, take 2 points that are closer and closer and closer together. Until finally, we wanted those 2 points to be so close together that the distance between them was 0. And we had to involve a limit to avoid division by 0. We have a similar situation here with second semester calculus, integral calculus, the calculus of finding the area under a curve. So if I want to find the area under a certain curve, I can chop up that area into a bunch of rectangles. And I can add up the areas of the rectangles. And if I want a better approximation, I can take more rectangles. And if I want an even better approximation, I'm going to take more and more and more rectangles until, for all intents and purposes, I use infinitely many rectangles. So that's what we did at the beginning of integral, well, the creators of integral calculus did. They said, what if I used infinitely many rectangles to cover that distance? To cover that interval from A to B. And they wrote this expression. Don't let it freak you out. The definite integral, so the area under a curve from A to B, is the limit, as you let the number of rectangles go toward infinity, of the sum. So here's sigma. Sigma just means sum. We're going to add up together. So like we've been doing, adding up a bunch of areas. And how do you find the area of a rectangle? Well, you multiply base times height. This has height times base. That delta x, that means a change in the input variables. Remember how we were subtracting x values, subtracting time values to find the width of the rectangle? Well, if you use more and more rectangles, they get skinnier and skinnier. So instead of actually thinking of it as a subtraction problem, we're just going to think of that as a tiny change in x. And we're going to multiply by the height of the rectangle. Well, the height of the rectangle comes from taking one of the x values on that interval and plugging it into the function. So c is just some letter we chose. C sub k means some number, c, from the kth interval. So for the kth rectangle, we're going to take that c value, we're going to plug it into the function, and that's what we're going to use for the height. Sometimes we use the left endpoint, sometimes we use the right, sometimes we use the middle. But imagine, if our rectangles are getting skinnier and skinnier and skinnier, pretty soon they're only going to be one function value wide. So that's what happens. It doesn't matter which point on that interval we plug in. Essentially, the rectangle's going to get so skinny, there's only going to be one choice. So, technically speaking, this is how we could find the area under a curve. So the founders of early calculus are like, whoa, 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 it's too ugly. We need a new notation. So Leibniz came up with this notation for the definite integral, a way of saying the area under a curve f of x. So I'm sure you've seen this symbol if you've been looking through your book or your love packet or your free response packet or anything. So this is the integral symbol, looks like kind of like a big S. So the integral from a to b, so the lower limit to the upper limit of f of x. This dx, you can tell where it comes from. Remember delta x in the sigma expression up top? Well, if delta x is a small change in x, dx is like saying an infinitely small change in x. So notice this is still written like height times width. Inside the integral, you should still see height times width, and that integral symbol just means I'm going to add up infinitely many of those products. So let's try it out. It's just a fancy way of saying the area under f of x between a and b. If we already knew that area, because we can use geometry, then the problem hasn't changed from when we used rectangles and other geometry in the last section.